All right. So, hello, grade 11 university physics students. This is Mr. Musklow. And as promised, I did record a video of today's lesson. So, with this video, you can still learn today's material even though I'm not at Opeongo. I did share yesterday that I'm going to Pembroke today with our Reach for the Top team. This video is actually on YouTube. I have a YouTube channel called Mr. Musklow, and in the past I have uploaded videos to my YouTube channel on days that I've been away. Whenever I taught at Valor, there was a stretch where I had to isolate because of COVID, and so I uploaded some videos to YouTube so that students could still learn some material while I was away. And so if you just actually look up Mr. Musklow on YouTube, you'll find my channel. And so you can just find this video there. This handout on acceleration near Earth's surface was passed out yesterday. So anybody that was not in class yesterday can find the handout in our missed handouts bin. Now, I shared yesterday that today's topic is actually a topic that I quite like. I find it interesting, and I'm actually a little sad that I'm not teaching it to all of you in person. But I definitely will have some comments to say about this material whenever I'm back at Opeongo tomorrow. Now, our previous lesson was on the Big Five equations. And we said yesterday that the Big Five equations can only be used in situations where an object is undergoing uniform acceleration. So it can only be used in situations where the object's acceleration time graph is completely flat and straight. You might well wonder, though, if there are actually many situations in real life where an object's acceleration time graph is truly straight and horizontal. A lot of examples in yesterday's lessons involved vehicles accelerating. So we imagined situations where someone hit the gas or the brakes in their vehicle, and that caused them to accelerate. But you might well wonder whether the acceleration time graph for an accelerating vehicle would actually be truly straight and horizontal. The answer is that in real life, the acceleration time graph for an accelerating vehicle is almost certainly not straight and horizontal. But interestingly, there is actually an everyday situation where an object really does accelerate uniformly. So they really do have acceleration time graphs that are flat and horizontal. And that situation would be an object that is under free fall. So as it explains in the handout, free fall is basically any motion that an object undergoes when gravity is the only force acting on the object. And we can see that we have a position, velocity, and acceleration time graph shown for an object that is thrown straight upwards. If you throw an object straight upwards, after it leaves your hand, gravity is the only force acting on the object. And so the motion that the object undergoes after it leaves your hand is what we call free fall. And so if I take an object and throw it straight upwards, we of course would expect the object to ascend to its maximum height. And then after it reaches its maximum height, it then falls downwards. And so that's what this position time graph is showing. Initially, of course, its position is 0. I throw it upwards, and its position increases, reaches this maximum, and then falls back down. Now, from this position time graph, we can construct a velocity time graph. And the velocity time graph for our object that has been thrown upwards actually looks kind of interesting. We can see that initially our position time graph has a steep positive slope, and so that corresponds to having a positive velocity. As time progresses, the position time graph levels out so that its slope becomes shallower and shallower. And then, interestingly, whenever it reaches its maximum height, the slope is zero. We can perhaps agree that the tangent at the very top of this position time graph would be horizontal, and so it would have a slope of zero. So when the object reaches its maximum height, it actually has a velocity of zero. This does make some sense if you think about it, right? If I throw an object upwards, it slows down and slows down and slows down until it reaches its maximum height. At the instant that it reaches that maximum height, it actually has a velocity of zero. And then, of course, after it has reached its maximum height, it then falls downwards. And so if we just think about the slopes of the tangents for our position time graph, we can see that those tangents would have slopes that become more and more negative. So they become more and more steep, more and more negative. And so we see this in our velocity time graph, the velocities become more and more negative. Okay, and this, of course, corresponds to our object speeding up as it falls downwards. Its velocity becomes more and more negative. Now, what's interesting about this is that our velocity time graph is just a straight line that slopes downwards. And so our velocity time graph always has the same negative slope. And so if we plot an acceleration time graph from this velocity time graph, it looks like this. And you can see that we do actually have an acceleration time graph here that is completely straight and horizontal. So it's important to understand that whenever we throw an object straight upwards, it actually always experiences the same acceleration. It's a very common misconception for students to think that when an object reaches its maximum height, its acceleration is zero at that instant. But that's not the case. It is true that the object has a velocity of zero whenever it reaches its maximum height, but its acceleration is always the same. And so, since the acceleration time graph for our object in free fall is straight and horizontal, we can actually use our Big Five equations from our previous lesson to analyze the motion of objects in free fall. So that's pretty cool, I think. But of course, before we actually start analyzing the motion of objects in free fall, we need to know what acceleration an object in free fall experiences. So what is the acceleration of an object in free fall? So to answer the question of what acceleration an object in free fall experiences, we need to talk a bit about the work of an Italian scientist named Galileo Galilei. I'll have more to say about Galileo later in this course. I think you can expect a Mr. Musklo original lesson after the March break on Galileo and Isaac Newton. Galileo was, in some ways, really kind of the first scientist that there ever was. He pioneered the scientific method. So I'll have more to say about him in Unit 2. So it's natural to think that if you have two objects of different masses and you drop those two objects at the same time, most people would expect the heavier object to reach the ground first. But Galileo showed in the late 1500s that this is actually not correct. He performed a simple experiment where he rolled balls of different masses down a smooth slope. Now, rolling masses down a smooth slope is not exactly identical to objects experiencing free fall, but the situation is similar, and Galileo did his experiment in this way because it was easier to observe since the speeds were smaller. And Galileo found in his experiment that each ball experienced the same acceleration regardless of the ball's masses. So balls of different masses actually rolled down the slope with the same acceleration. Now, I would expect some students to likely think at this point that this simply is not right. It totally defies our common sense to imagine that if I drop two objects that have different masses, those objects experience the same acceleration. And so the back of our first page just talks a bit about some misconceptions so that we can just better understand what's really happening here. Let's ask an interesting question. If I drop a hammer and a feather, which object will hit the ground first? I think that most people would predict that the hammer will hit the ground first, and that is certainly correct. If you actually took a hammer and feather and dropped them, the hammer would hit the ground before the feather. So how can we really make sense of Galileo's experiment? Galileo is suggesting that objects of different masses experience the same acceleration, but that's clearly not true for our hammer and feather. So what's going on with our hammer and feather? The answer is that the feather takes longer to reach the ground because it is affected more by air resistance than the hammer is. If you actually completely remove air resistance from the situation and drop a hammer and feather in a vacuum where there is no air, they will actually hit the ground at the same time. The astronaut David Scott actually demonstrated this in the Apollo 15 moon mission. On the moon, there is no air because the moon does not really have an atmosphere. So if you drop objects on the moon, they are not influenced at all by the effects of air resistance. And so in a demonstration, the astronaut just held out an actual hammer and feather on the moon and dropped them at the same time. And you can very clearly see that the objects experience the same acceleration. So they both hit the ground simultaneously on the moon. You can look this up on YouTube. If you just look up hammer, feather, moon on YouTube, I'm sure that you can find a video. So we'll watch the video tomorrow together. But it is quite cool to see a feather and moon accelerate the same amount in the absence of air resistance. There's some interesting physics happening there. Now, this section in the handout just explains a common misconception that people have about the physics of free-falling objects. So I've told you that if you drop a hammer and feather in the absence of air resistance, the hammer and feather will hit the ground at the same time. But even without air resistance, many people actually find that very difficult to believe. Because if you hold a hammer in one hand and a feather in the other hand, you can very clearly feel the hammer pushing harder on your hand than the feather. Right? The hammer has more weight. it's pushing with a greater force on your hand. And so you can actually feel a much greater force of gravity acting on the hammer than the feather. And so most people just assume then that that greater force of gravity would pull the hammer to the ground faster. So wouldn't that happen? If you have a greater force of gravity acting on the hammer, wouldn't that pull the hammer to the ground faster? And the answer is no. To explain why, I give students kind of a weird analogy that I came up with when I was teaching this topic at Valor. So I acknowledge that this is kind of a weird analogy, but just stick with me for a minute. I want you to imagine that there are two fridges sitting in front of you. Why fridges? I don't know. Fridges are objects that you might want to push across the floor. Really, any object that you are pushing across a floor could work. I'm just saying fridges. So just imagine that there are two fridges in front of you. One fridge is loaded with food, and the other fridge is completely empty. So this means that one fridge has a much greater mass than the other. And now let's suppose that you want to accelerate both fridges equally by pushing on them. So you have a heavy fridge and a light fridge in front of you, and you want to accelerate them equally by pushing on them. I think we can probably agree that if you actually wanted to accelerate the fridges equally, you would need to push with a greater force on the fridge that is loaded with food. Right? The heavier fridge would require a greater force to accelerate it. The reason why I use this weird analogy is because when we push on the fridges and accelerate them equally, we actually have a situation where two objects of different masses have different forces acting on them, but they are accelerating equally. That is what happens with our fridges. Okay, now our falling hammer and feather are in the exact same situation. Our hammer and feather have different masses. There are different forces acting on them, but they accelerate equally. So it's kind of weird to think about, but it really is true that in the absence of any air resistance, objects of different masses actually experience the same acceleration when they are in free fall. So just to be clear, in this course, we're always going to neglect air resistance whenever we analyze the motion of free-falling objects. Now, this might seem to be like an oversimplification. We've said that the motion of a falling feather is very much affected by air resistance. But this approach actually isn't very crude for many situations. Feathers are absolutely affected significantly by air resistance. But if we think about objects like rocks or textbooks or basketballs instead, if you drop these sorts of objects from shoulder height, their motion is actually affected very little by air resistance. So it's actually very reasonable to just neglect air resistance when you analyze their motions for most purposes. Okay, so this does mean, by the way, that if you take a textbook in basketball and drop them from shoulder height, they will actually hit the ground at the same time, even though they have very different masses. You can try this for yourself if you don't believe it. Whenever I'm back at Opeongo tomorrow, I will definitely show this to you in person. Not with textbooks and basketballs exactly, but with other weights. Okay, so that's all quite interesting, I think. Objects in free fall experience the same acceleration regardless of their mass. So what is the acceleration, though, of an object in free fall on Earth in the absence of air resistance? Well, it actually is going to have slightly different values depending on where you are on Earth. If you're on the top of a mountain, then the acceleration from Earth's gravity is going to be slightly less than if you're at sea level. The farther away you get from Earth's center, the smaller the value of the acceleration. No matter where you are on Earth's surface, though, the acceleration always rounds to 9.8 meters per second squared down. It always rounds to that value. And so we are going to use that value in the problems that we look at in this handout. So that's a value that you're actually going to use a lot in this lesson and this unit and really this course. It's going to be used a lot in Unit 2 as well. So you'll definitely have 9.8 meters per second squared committed to memory shortly. One last comment that I'll make before we look at our first worked example. I'll just mention that whenever you solve problems for objects that are in free fall, as always, we need to assign a direction as positive. And my suggestion is for you to just always assign up as positive. If you're just consistent all the time in assigning up as positive, you're less likely to get mixed up with whether your numbers are positive or negative. So I always set up as positive whenever I'm doing these sorts of problems. But if you want to be a rebel and set down as positive, you go for it. Okay, so in the remainder of the handout then, we're just going to look at some examples that involve free-falling objects. You'll see that these problems really boil down to using the same equations as we had used in our previous lesson. But in problems involving free-falling objects, we sometimes need to read into the question a bit more to actually get some more information from it, as we're going to see. So we'll start out with this example. I'll just read it. It says, while bouncing a basketball, Mr. Musklo throws the ball downward with an initial velocity of 5.2 meters per second down. The ball travels 0.84 meters down and hits the ground. What is the basketball's final velocity when it hits the ground? Okay, so we imagine that Mr. Musklo is bouncing a basketball, say in the student-teacher basketball game, and while bouncing it, he throws the ball downward with an initial velocity of 5.2 meters per second down. The ball travels 0.84 meters down before hitting the ground, and so we need to find the basketball's final velocity when it hits the ground. Now, when this question asks for the basketball's final velocity when it hits the ground, it's actually common for students to think that the answer is just 0 meters per second because the ball comes to an abrupt stop when it hits the ground. Okay, and students often give this as an answer when they first start doing these sorts of problems. The basketball absolutely does come to an abrupt stop when it hits the ground. But that's not really what the question is asking for. The ball picks up speed as it falls downward, so the question really wants to know what velocity the basketball has at the instant that it strikes the ground. So what velocity does it hit the ground at? Okay, so as I've said, my suggestion is for you to set up as positive. If up is positive, then our initial velocity is minus 5.2 meters per second because that velocity was in the downward direction. The displacement is minus 0.84 meters. And here's the thing, we actually know something else, which is that the object is accelerating at minus 9.8 meters per second squared. So that's another piece of information that we have drawn from this question. So we know VI, delta D, and A, and the question is asking for VF. And so we need to identify our big five equation that has these four variables. And if you look in the table in our equation sheet, you can see that equation 5 meets that criteria. So this is equation 5. Now I want to solve for VF in equation 5. That's pretty straightforward. All I need to do is just square root both sides. So if I square root both sides, I get this equation. And so I can plug in our values, and we get an answer of 6.6 meters per second down. Now, as it explains in the handout, when we punched our numbers in, we actually took the square root of 43.5. And we should always remember that when you take the square root of a number, the answer can be positive or negative. So positive 6.6 is a solution, as well as negative 6.6. And in this case, we're actually using the negative square root as our answer, because it's clear that the final velocity for our object would be in the downward direction. The positive answer doesn't make sense. The final velocity clearly wouldn't be in the upward direction if I'm throwing the ball downward. Now you'll notice that this solution has a new symbol that we haven't seen yet in this course. This arrow in mathematics means implies that. So basically what I've written here is that the equation VF squared equals VI squared plus 2A delta D implies that VF equals the square root of VI squared plus 2A delta D, rather. So I'll often use this implies that symbol whenever I'm solving for the variable that we need. So moving forward, I'll do this often where I write our original equation, and then I'll just put this implies that symbol and write what the variable that we are looking for equals according to that equation. So again, all I've done from here to here is just solved for VF. And so this first equation implies that VF equals that. Okay, so that's our first example. Again, it really just amounts to using our big five equations, except the object is in free fall. So it has an acceleration of minus 9.8 meters per second squared. Okay, so let's look at another example then. I'll read this one out loud. So this example says, Mr. Musklo throws a tennis ball upwards at a velocity of 8.0 meters per second up. The ball travels upwards, reaches its maximum height, and then falls and hits the ground. This is a two-part question. There's a part A and B. A asks, how long does it take the ball to reach its maximum height? So that's kind of an interesting question. How long does it take the ball to reach its maximum height? Okay, so let's start out by writing what we know. As before, we'll set up as positive, and so we'll write that VI is positive 8.0 meters per second. And then the acceleration, of course, is minus 9.8 meters per second squared. So those are two pieces of information that we can draw. But we need three, of course. So how do we proceed from here? Well, the key to finding how long it takes the ball to reach its maximum height is to understand that when the ball reaches its maximum height, it actually has a velocity of 0 meters per second at that instant. We can see this if we look at the graphs in the beginning of our handout. Right, so here's our position time graph. Our object rises to its maximum height and then falls down. And we've said that at the instant that the object is at its maximum height, it has a velocity of 0 because the slope of this position time graph is 0 at that time. Right? The tangent would be completely flat here. And so this is why our velocity time graph shows a velocity of 0 when the object reaches its maximum height. When the object reaches its maximum height, it's kind of switching directions. It's going from moving upwards to moving downwards. And so at the instant that the object is switching directions, it actually has an instantaneous velocity of 0 meters per second. Kind of weird to think about. So that's the key to solving our problem then. Our third piece of information is that Vf equals 0 meters per second. So Vf equals 0 meters per second in this problem. Okay, so the question asks for delta t, and so we need to find the equation that has Vi, A, Vf, and delta t. Equation 2 meets that criteria. And so if I solve for delta t in that equation, I get this. And then if I plug our values in, we find that delta t is 0.82 seconds. So it takes 0.82 seconds for the tennis ball to reach its maximum height. Okay, so that's kind of cool, I think. Some interesting physics. All right. I would ask at this point if anyone has any questions, but this is a pre-recorded video, so I can't really do that. So certainly if there are any questions, I can answer them when I'm back tomorrow. For now, though, we'll just move on to part B in the example. All right, so part B asks, how long does it take the tennis ball to hit the ground if the ground is 1.35 meters below the height where it was thrown? Okay, as before, we're going to just write down what we know and go from there. So we're going to set up as positive. Vi in the problem was positive 8.0 meters per second. And the acceleration, of course, is minus 9.8 meters per second squared. We can also write that delta D is minus 1.35 meters. This is the displacement that our tennis ball experiences from its motion. We should remember that a displacement vector points from the initial position to the final position. So it says in this question that the tennis ball hits the ground 1.35 meters below the height where it was thrown. And so the displacement vector that points from where the ball started to where it ended would be a vector that points 1.35 meters down. And so that would be written as minus 1.35 meters. Okay, so we have Vi, A, delta D. Question asks for delta T. And so we need to identify the equation that has these four variables. That is equation 3. Now, solving for delta T in equation 3 can get kind of messy because this is actually a quadratic equation for delta T. You can see that we have a term with delta T as well as a term with delta T squared. And so we actually need to use the quadratic formula to solve for delta T in this example. And so this is partly why we reviewed the quadratic formula in our math skills handout. You do need the quadratic formula to solve some of these problems. Okay, so here we go. I'll plug in our values into the equation. And then we rearrange it so that it's in the form a delta t squared plus b delta t plus c. And then we insert a, b, and c into our quadratic formula. And we find that one solution is that delta t equals minus 0.15 seconds. Another solution is that delta t equals 1.8 seconds. Now, we're probably used to the idea that whenever you use the quadratic equation, you always get an answer that doesn't make sense. A negative answer doesn't make sense, obviously. Delta t of minus 0.15 seconds is 0.15 seconds before the ball was even thrown. So that doesn't make sense. 1.8 seconds is clearly our answer. And so we can write that it takes 1.8 seconds for the tennis ball to hit the ground. Now, I did just include an explanation in this handout for why we actually got two solutions for delta t, because I think it's actually helpful for students to understand this. So when we use the quadratic formula in this example, one of these solutions was minus 0.15 seconds, and the other solution was 1.8 seconds. So what does a solution of minus 0.15 seconds mean? Why did we get that as an answer to this problem? Well, we can actually see where this comes from if we plot the displacement of the tennis ball as a function of time. And so that is shown in this image. I actually plotted the displacement of the tennis ball as a function of time. And so just to be clear about what's happening in this graph, at a time of 0, the ball's displacement is clearly 0 because it hasn't left my hand yet. And then it reaches its maximum height at 0.82 seconds. We found that in part A. And then at 1.8 seconds, it has a displacement of minus 1.35 meters. So at 1.8 seconds, the ball reaches a position that is 1.35 meters below where it started. But here's the thing. We can see that 1.8 seconds is a valid solution to this problem, but mathematically, you do also have this minus 0.15 second solution as well. Now, of course, the ball never actually has that displacement at minus 0.15 seconds because this is 0.15 seconds before the ball was thrown. We throw the ball at this instant. And so this is actually before the ball was thrown. So the ball never has that displacement at minus 0.15 seconds in reality, But this is a valid mathematical solution to our problem. So we can think about it mathematically, even though, it doesn't actually make physical sense. Okay, again, I would ask at this point if there are any questions, but this is a pre-recorded video. Okay. So I know this lesson has been kind of on the long side, as was yesterday's. There is one more example, but this one's pretty short. It's not as long as the previous two-part example. So this is our last one. I'll read it out loud. This example says, Mr. Musklo drops a rubber ball from a height of 1.42 meters above the ground. How long does it take the rubber ball to reach the ground? This is a good example to end with because it might not really appear that we're actually given hardly any information in this problem. The only number that we're actually given is this 1.42 meter number. But again, let's just write down what we know here. We'll set up as positive. The rubber ball's displacement is minus 1.42 meters because its displacement is 1.42 meters down. A is minus 9.8 meters per second squared. So we've written two pieces of information. We need a third. So what else are we given in this problem? Well, the key to solving this problem is to just note that the ball is not thrown upward or downward. It doesn't say in this question that the ball is thrown up or down. It just says that it's dropped. So it's just basically released from its height above the ground. And here's the thing. If you aren't throwing the ball up or down, it will actually have a velocity of 0 meters per second at the instant that it is released. The tennis ball in our previous question was actually in the same situation whenever it reached its maximum height. The tennis ball in our previous question had an instantaneous velocity of 0 meters per second when it reached its maximum height. Likewise, in this example, our rubber ball has an instantaneous velocity of 0 meters per second at the instant that it is released. Okay, so we can actually write that our initial velocity in this problem is 0 meters per second. Question asks for delta t. And so we need to identify the equation that has our variables. This is actually equation 3 again. So here's equation 3. So, oh dear, we have equation 3 again. This equation is quadratic in delta t. And so you might think that we need to use the quadratic formula again, but we actually don't. We actually don't. The reason why we don't need to use the quadratic formula is because VI is 0. And so this entire term with VI just disappears. Right? This VI delta t term equals 0. And in physics and mathematics, we often put arrows with a 0 through parts of our equation that just disappear as a result of variables equaling 0 in the equation. So you'll see me write this sometimes, where we have terms that equal 0, and so I can just write our arrow with 0 to show that that part equals 0 and goes away. Okay, so this actually makes our life easier. If this part disappears and goes away, then we're just left with delta d equaling half a delta t squared. And solving for delta t is straightforward now. We don't need to use the quadratic formula. I can solve for delta t we find that delta t equals the square root of 2 delta d over a. And so if I plug our values in, we find that delta t is 0.54 seconds. And so our rubber ball dropped from a height of 1.42 meters above the ground, takes 0.54 seconds to reach the ground. Okay, and actually just be concrete, 1.42 meters, that's kind of like shoulder height. So if you drop an object like a rubber ball or a basketball or textbook from shoulder height, it'll take about half a second to reach the ground. So there you go. Okay, so as I've been saying, I would ask at this point if there are any questions, because I'm just, doing it by habit here. When I'm finished a lesson, I like to ask if there are questions. But again, this is a pre-recorded video, so I can't really take questions right now because I am currently recording this video on Monday evening. So I will take questions tomorrow. Certainly at the beginning of tomorrow's class, I'll just ask if anyone has any questions about this material. In the meantime, you can just try working through these textbook questions. You'll see that there are actually quite a few questions provided, but some of them are kind of repetitive. So the ones in italics are kind of optional just if you're looking for more practice. Okay, so that's it. That is our lesson on acceleration near Earth's surface. Good luck with the textbook questions, and I'll see you tomorrow.